Hello, I am Anshu Sharma from Randolph-Macon College, and today I will be presenting on the commutativity of noisy matrices, or matrices with noise added. This research was supported by NSF Grant 2012216 and performed under the supervision of Professor Brian Sutton and alongside fellow students Megan Gunn, Casey Kent, and Eric Marks, all from Randolph-Macon. So, what are the properties of commuting matrices? Well, if two matrices commute, the matrix product A times B equals the matrix product B times A. Another way of saying this is to say that commutator, or the difference of the matrix products AB minus BA, equals 0. What if the commutator is non-zero, but small? Then we can consider the ideas of nearly, or almost commuting matrices. So let's review some terms from linear algebra topics. Let A be a square matrix, let lambda be a scalar, and let V be a vector. If the product A times V equals the product lambda times V, then we say that lambda is an eigenvalue of A and that V is an eigenvector of A. If X is equal to A plus BI, then the complex conjugate is X bar, which is equal to A minus BI. The conjugate transpose A star of the matrix A swaps the rows and columns and takes the complex conjugate of each element. If A equals its conjugate transpose, or if A equals A star, then we say that A is Hermitian. If A is Hermitian, then A would be equal to a matrix S times capital lambda times S star, where S is a matrix whose columns are A's eigenvectors, and capital lambda is a matrix with A's eigenvalues on its diagonals. Also, note that S star times A times S would be equal to capital lambda, indicating A is diagonalizable. The matrix 2 norm returns the largest singular value of the matrix. A singular value is comparable to an eigenvalue but also exists for non-square matrices. The matrix Fouriern's norm returns the square root of the sum of the squares of the elements. Now let's define the terms nearly commuting and almost commuting. If a pair of matrices A and B is almost commuting, then the 2 norm of the difference AB minus BA is less than some epsilon for a small epsilon. What is small? That definition may vary. If a pair of matrices A and B is nearly commuting, then for small delta A and delta B, also referred to as noise matrices in this presentation, the matrices A plus delta A and B plus delta B will commute. Again, what is small? We can consider or say the 2 norms of the noise matrices to be smaller than some epsilons, but again, the definition of small may vary. Pearcy and Shields, in a 1979 paper, write this theorem linking nearly and almost commuting matrices. If two matrices are almost commuting for epsilon squared, there exist noise matrices such that they are nearly commuting on the order epsilon. Now let's consider 4 measures of commuting matrices. Measure 1. The 2 norm of the difference AB minus BA is smaller than epsilon 1 for small epsilon 1. That is, A and B are almost commuting. Measure 2. For delta A, whose 2 norm is less than epsilon 2, and delta B, whose 2 norm is less than epsilon 3, A plus delta A and B plus delta B commute. That is, A and B are nearly commuting. Measure 3. There may be an eigenvector matrix V, for which the sum of all elements in V star times A times V minus the trace of V star times A times V is less than epsilon 4, and the sum of all elements in V star times B times V minus the trace of V star times B times V is less than epsilon 5. Another way of saying this is that V star times A times V and V star times B times V are almost diagonal. Measure 4. There may be a U and V, for which U star times A times U and V star times B times V are diagonal, and the 2 norm of U minus V is less than epsilon 6. So for those of you who are keeping count, that's 6 epsilons. And the overarching question is, to what extent are these epsilons the same? So, how can we generate the noise delta A and delta B? We can use in MATLAB the function k times random of n, where n is the matrix size and the argument of random. Random is a MATLAB function that generates an n by n matrix of random numbers from the standard normal distribution, and k is a scalar, a power of 10. We can then add this noise matrix to a commuting matrix. Using random to generate noise matrices and running several trials on MATLAB led to this finding. The norms of the commutator of two commuting matrices with noise added are one order of magnitude greater than the largest order of magnitude of the norms of the noises of the commuting matrices. What does all this mean? Well, first, let's note that norms refers to both the 2 norm and the Frobenius norm, even though the notation on this slide will only refer to the 2 norm. Secondly, note that A prime, or A with the tick mark, is the sum of A and delta A, and B prime is the sum of B and delta B. A and B are the original commuting matrices, and delta B and delta A and delta B are the generated noise matrices. Let's look at some examples. If the 2 norm of delta A is on the order of 10 to the negative 11 and the 2 norm of delta B is on the order of 10 to the negative 10, the 2 norm of the commutator of A and B will be on the order of 10 to the negative 9, one order of magnitude greater than 10 to the negative 10. If the 2 norm of delta A is on the order of 10 to the negative 11 and the 2 norm of delta B is on the order of 10 to the 0, then the 2 norm of the commutator of A and B will be on the order of 10 to the 1. This links notions 1 and 2, those of nearly commuting and almost commuting matrices. The theorem by Pearcy and Shield suggests that not all matrices behave like this. For example, Pearcy and Shield's theorem suggests that there exist perturbations delta A and delta B whose 2 norms on the order of 10 to the negative 5, such that the 2 norm of the commutator of A prime and B prime is on the order of 10 to the negative 10. So let's review the 4 measures of commuting matrices. Measure 1, A and B are almost commuting. In this case, the commutator is small but non-zero. Measure 2, A and B are nearly commuting. The commutator is 0 with added perturbations to one or both matrices. Measure 3, there exists a matrix V such that V star times A times V and V star times B times V are almost diagonal. And measure 4, there may be a U and V for which U star times A times U and V star times V are diagonal, and the 2 norm of the difference U minus V is small. The overarching question is, once again, to what extent are these measures linked? So what are some additional directions to continue this research? One direction is to use the dodo function written by Professor Brian Sutton to link measure 1, almost commuting matrices, and measure 3, common eigenvector matrices of matrices that are almost diagonalizable. We can add noise to commuting matrices and use dodo to generate a quote-unquote common Hermitian eigenvector matrix and almost diagonal matrices. A second option is to use the eigen function to link measures 1, almost commuting matrices, and 4, diagonalizable matrices that have almost the same eigenvector matrices. We can add noise to commuting matrices, use eigen to generate eigenvector matrices, and compare with eigenvector matrices of the non-noisy matrices. And the third course is, given matrices A and B, can we use the 2 norm of the commutator to find delta A and delta B such that A plus delta A, such that the commutator of A plus delta A and B plus delta B is 0, and such that the such that the 2 norms of the added perturbations delta A and delta B are minimized. This can be thought of as working backwards. Instead of going from noise to a commutator, we are going from a commutator to a specific perturbation. See the Pearcy and Shields paper for more details. The references consulted for this research and presentation are Numerical Matrix Analysis, a 2009 textbook by Ibsen, Fundamentals of Matrix Computations, a 2010 textbook by Watkins, and Almost Commuting Matrices, a 1979 paper in the Journal of Functional Analysis published by Pearcy and Shields. Thank you for listening.